The only difference is in this lesson, we're just going to be extending our work with sine and cosine functions derivatives. Tomorrow, expect a little quiz. And it would just be probably a question similar to the stuff that we did yesterday, not like the one that we just did. But if you were to go back and look at any of the examples we did yesterday, that's probably a good, fair quiz question tomorrow. And then also we will have a quiz question tomorrow, very similar to something from example 2 today. Okay, probably about 20 minutes. It's not, if you know the rules that sine has a derivative of cosine in general and cosine has a derivative of negative sine, and you know your chain rule and your product rule and all that, it's just you get to work on it and you do it. Take a minute and double check your work and you're done. The difference is today we're going to be continuing to look at derivatives of sine and cosine functions in terms of graphs. We're not going to delve too deep into the graphical properties of these functions because it will just take too long, and you'll get my drift in a few minutes. We're also going to be looking at implicit differentiation. So to begin with, this is just telling you what we're doing. We're going to use this stuff to do more problems. Problems that involve equations of tangents, max-mins. Well, we're not going to do any examples with max-mins or concavity because those are the ones that take too long. But from not day one, but as soon as we knew about what this course was about and calculus was about, determining equations of tangents was a big deal, right? We started off by doing it with limits, and then we found out there's this thing called the derivative. Well, we're going to start with an example like that today. Determine the equation of the tangent to this function at the point where x is pi over 6. Now, we can take a look at that function if you like. This function as a graph is something that's beyond Math 30-1. We can take a look at it. So on your graphing calculator, you can enter y equals cosine of x over sine of 2x. We definitely always want to be in radians in this course. I cannot conceive of a simple, well, I almost misspoke. It's very rare that you would want to be in degrees. Maybe if you just had a triangle where you had to find an angle in the corner of a triangle and you were going to use the sine law or the cosine law, and you just want to know how many degrees it was, that's fine. But in terms of algebra and calculus, always in radians. So I'm going to go y equals cos of x divided by sine of 2x. And I'm going to go zoom trig. And we get a graph which is not familiar at all to you. This is actually a graph of a reciprocal trig function that's kind of disguised. It has a series of vertical asymptotes at different places. It has no x-intercepts and it has no y-intercepts. We can use our calculator, by the way, to find the equation of the tangent at pi over 6. If you just want to know the slope of the tangent, you can go to your calculate menu and choose dy dx and enter the x-coordinate of the point of tangency, which is pi over 6. Okay, so the slope is that. Now that number, I recognize that number. That happens to be the negative of the square root of 3. Okay? There's no way for you to convert it to an exact value unless you kind of have an idea of what it is. If you want to know the actual equation, I'm just going to park this here so we can use it later, just to confirm things. If you want to know the actual equation, then instead of going to your calculate menu, you go to your draw menu. You go second program and you choose draw tangent. You still have to enter the x-coordinate, but the difference is here it's going to draw the tangent, and instead of just giving you the slope, it will give you the equation of the tangent. You're probably not going to be allowed to use these calculators for this kind of thing in post-secondary, but we can use them as a learning tool right now, right? So I still have to enter the x-coordinate of pi over 6. And it grinds away, it draws the tangent line, it gives me an equation. Now, I don't know exactly what that is. I can't read all of the decimals. There's probably a way to pull it up on the main screen, but it doesn't matter. I'll just park this over here as well. And that equation of that tangent line is given in the y equals mx plus b form. Now, let's get back to the matter at hand. In order for you to determine the equation of a tangent line, the way I've taught it, if it were grade 10, I'd say you need to know the slope and the y-intercept. That's not what we do here. You need to know the slope and a point on the line. Well, the slope is going to be f prime of pi over 6, right? That goes way back. You should know that already. The only thing that's different here is we're using trigonometry. The point will be pi over 6, comma, f of pi over 6. Not f prime of pi over 6, but just f of pi over 6. So let's find that y-coordinate first. Let's take our function. I'm just going to go to a clean surface here. Y equals cosine of x over sine of 2x. The y-coordinate, y1, will be equal to cosine of pi over 6 over sine of 2 times pi over 6. So what are we talking about here? Pi over 6, my lumpy circle there, has a terminal arm that terminates at this point, which has coordinates of root 3 over 2, comma 1 over 2. So cosine of pi over 6 is the x-coordinate, which is root 3 over 2. It's going to work out very nicely for a y-coordinate. The sine of 2 times pi over 6, well, 2 times pi over 6 is pi over 3. And when you look at pi over 3 has a terminal arm which intersects the unit circle at that point. It's not a perfect drawing, I get that. And the coordinates here are 1/2, comma, root 3 over 2. And the sine is the y-coordinate of the point of intersection, which is root 3 over 2. So, we kind of we got lucky here. y1 is 1. So now what we know is the point is pi over 6, comma 0. Now, we need to find the slope as well. We've got the point. We checked that box. Now we need to know f prime of pi over 6, which means we can find f prime of x first. Not often that I use prime notation, but I'm going to. I just want to look at it one more time to make sure I have it in my head. I'll write it here so you can follow along if you're watching this later. So the derivative of the top is negative sine of x times the bottom, which is sine of 2x, minus the top, which is cos of x, times the derivative of the bottom, which is cos of 2x, times 2. Are we fine with that so far? We still have to divide by the bottom squared. Yeah. Thank you. After all that talk of the only thing that could be simpler is 0, I wrote 0 instead of 1. Yes, the y-coordinate is 1. I hope you understand this whole implied bracket thing. When I write cos of 2x times 2, a little common sense goes a long way. That 2 at the end is not multiplied by the 2x. That's an external kind of coefficient. This is over the bottom squared. Now, you could certainly argue that we don't need to simplify anything because we're just going to put in pi over 6. I'm going to simplify it a little bit by, well, all I'm going to do is this. I'm just going to squeak that 2 out in front of the cosines. Are we fine with that? Okay. Now, I'm not going to draw a unit circle diagram for each one of these. We know what pi over 6 has for coordinates and what pi over 3 has for coordinates. I'm also just reminding you that x is pi over 6 and 2x would be pi over 3. All right? And I'm not looking at a unit circle. You can look at a unit circle, but between all of us, I want you to check my thinking here. When I talk about f prime of pi over 6, this will be negative sine of pi over 6, which will be negative 1/2 because sine of pi over 6 is 1/2. Sine of 2x will be sine of pi over 3, which is root 3 over 2. Minus 2 times cosine of pi over 6. Cosine of pi over 6 is the x-coordinate at pi over 6, which is root 3 over 2, times cosine of 2x, which is pi over 3. The cosine at pi over 3 is the x-coordinate there, which is 1/2, over sine of 2x, which is the sine at pi over 3, which is the y-coordinate, which is root 3 over 2. Yeah. Squared. Thank you. So that's where we're at. We clean it up a bit. What I get is on the top, negative root 3 over 4, minus 2 root 3 over 4. I didn't bother to cancel a 2 with the 2 on the top because then I get a common denominator. Over 3 over 4, because root 3 squared is 3. This gives me negative 3 root 3 over 4 over 3 over 4. This is negative 1 root 3 over 4, and we're subtracting 2 root 3 over 4. So we get negative 3 root 3 over 4s. Multiply top and bottom of this little fraction by 4. The 4's cancel. The 3 on the top cancels with the 3 on the bottom. The slope, all we're left with is negative root 3, which matches, by the way, going back up here, what we had for the slope. Remember I told you I recognize that as root 3, negative root 3. You can, if you want, take your calculator and go root 3 and convince yourself you get 1.73 something. So now all that's left is to take that slope of negative root 3 and the point of pi over 6 comma 1 and feed them into this equation. So I'm going to have y minus the y-coordinate equals the slope times x minus the x-coordinate So the y-coordinate was 1, the x-coordinate was pi over 6, and the slope was negative root 3. I think that looks good. Don't try to get rid of this 6 in the denominator right now because it's buried inside of brackets. Multiply it out first to expose it. I would prefer to write pi root 3 rather than negative root 3 times pi. The reason is you can easily maybe think that the pi goes under the root, but if you put it out in front, there's no question that it's a coefficient. I can multiply everything by 6 now and get 6y minus 6 equals negative 6 root 3 x plus pi root 3. I guess I'm kind of done with this question. Whatever you want to do with that, feel free. Zero the equation. If you want to rearrange it for y, I don't like that, but you could. Just double check times 6 times 6 times 6 times 6. So 6 root 3x minus 6y plus 6 plus pi root 3 equals 0. Just a second here. No. I moved everything to the left side. My mistake. These are both negative. No, wait a minute. Then this is positive. So I'm moving everything to the left side. The x's become positive. The y's are already there, and they stay positive. The 6 is already there. It stays negative. The pi root 3 becomes negative when I move it over. I got my signs all backwards there for a second, but I got it back. Are we okay with that? That's an exam question. I would say it's maybe a written response question. There's a fair bit of running around to do. I think it's a little too ambitious for a numerical response or a multiple choice. All right, let's take a look at a couple more examples. I had to retype this lesson because I changed it slightly. Is this the same relation that you have? Okay. Who knows what it looks like? You can't even graph this on your calculator because you can't rearrange it for y. Let's differentiate it. The derivative of sine of y is cos of y. Is that correct? Is the derivative of sine of y cos of y? Nope. It's cos of y dy dx. And I admit, when I said is the derivative, well, it depends. The derivative with respect to what? With respect to x. So you have to multiply by the derivative of the argument with respect to x. The argument is y, so that's dy dx. Minus sine x is the derivative of cos x with respect to x. Negative sine of x. Yes. If you want to push it and say, yeah, but don't we have to multiply by the derivative of the argument? Okay. You're then multiplying by the derivative of x with respect to x, which is 1. And this is equal to 0. Simple problem. Rearrange for dy dx. Move the sine x to the other side where it becomes positive. So dy dx equals sine x over cosine y. Okay, cos xy plus cos squared x equals sine y. This one I'm going to graph. It's pretty complicated, isn't it? It's really pretty complicated. There are certain glitches in this, like some of those shapes appear to have breaks in them, but they shouldn't. How do we find the derivative of cosine of xy? Well, it's the negative sine of xy times the derivative of xy. Right? The derivative of a cosine of a thing is the negative sine of the thing times the derivative of the thing. And xy is a product. The derivative of x times y plus x times the derivative of y. There's our goal, dy dx. What is the derivative of cos squared of x? It is 2 cos of x times negative sine of x. How come? Because cos squared of x is cos of x quantity squared. So it's a power. I move that 2 in front of the cos of x, drop 1 from the exponent, then multiplied by the derivative of cos of x, equals sine of y. Well, the derivative of sine of y is cosine of y times dy dx. So the derivative of cosine xy is negative sine xy times the derivative of xy. And the derivative of xy is found by considering xy to be a product of x and y, so you apply the product rule. Derivative of x times y plus x times dy dx. Plus, again, cos squared of x is cos of x quantity squared, so we apply the power rule followed by the chain rule. And then sine of y, we apply the rule for the derivative of sine and the chain rule. Are we good with that? Okay. I mean, that's pretty amazing. I mean, we're not here to pat ourselves on the back all the time. But look at the math we're dealing with and we've been dealing with in this course so far. You guys have come a long, long way. It's university level. That's what it is. So now how do we get the dy dx by itself? This dy dx is buried right now. We need to take this and expand this first term out so that we have dy dx terms that are separate from other terms, which gives us negative y sine xy minus x dy dx sine xy minus 2 sine x cos x. I mean, you could put sine 2x there, but I don't... What's to be gained by doing that? You could. Equals cos y dy dx. So now what we need to do, everybody, is move all of our terms that have the dy dx, move all of these terms to one side and these terms to another side. And we want to do this in such a fashion that we minimize the number of negatives. And I don't think it really matters. I think we're going to have 2 negatives regardless of the side we move things to. Those of you in Math 30-1 right now, what we are going to be doing tomorrow has a very similar strategy to it. And those of you that have taken 30-1, I'm talking about solving equations where you've taken the log of both sides and moved exponents down, and you have to get the x's on one side. You might have to expand things out and shuffle the terms into 2 piles. So it doesn't really matter. I'm going to put my dy dx's over here on the right, and I'm going to get x dy dx sine of xy plus cosine of y dy dx is equal to negative y sine xy minus 2 sine x cos x. Boy, and there's x's and y's there. I want to go back and just double check everything. Sine xy times negative y, that's okay. Yeah, I think we're okay. Negative sine x, y, and the y are on the left. Negative 2 sine x cos x are on the left. Cos y dy dx and x dy dx sine xy are on the right. All we have to do is factor out the dy dx and divide by whatever we're left with, and we're done. And that leaves us with the derivative of y with respect to x of negative y sine xy minus 2 times sine x sine y, nope, times sine x cos x over x sine xy plus cosine of y. So, so if you knew the coordinate pair x comma y for a particular point on the graph of this relation, you would put those numbers in, and it would have to be in radians, to find the slope. But, you know, here's even a question for you. Forget about the derivative and the slope. Imagine me just saying, oh, x equals pi over 6 rads. What is y equal to? Like, how would you even find out what y is equal to? I don't know. I'd have to try it, and I don't want to. Okay? The first question in number 2 is basically reintroducing you to implicit differentiation. The second question is testing your algebra skills, right? There's quite a bit of work going on here. Don't even think about trying to simplify this. Like I said, if you wanted to write this as sine of 2x, okay, but what does it gain you? Finding critical numbers? Forget it. How would you find the values of x comma y that make this 0 or undefined? You wouldn't. So on page 314, number 2, 2, 3, and 14. 2 is some implicit differentiation, so you can practice that. 3 is finding equations of tangents, so you can practice that. 14, sorry, did I say 14? I meant to say 13. Does yours say 14 or 13? 13. So 13 is just an extra practice one. I'll change that right now so I don't forget to change it later. And by the way, if you go back to this, and I'll be quick. If you go back to this, and nobody said anything, so I don't know. Maybe it didn't occur to anybody. We did not have to find the derivative by doing all of this. Because, and I can tell by the looks on some of your faces, some of you knew this, y is equal to cos x over sine of 2x y is equal to 1/2 sine of x to the negative 1. Never, ever write this to mean sine of x quantity to the negative 1, because this means inverse sine. It means something different. Doesn't get much simpler than that to differentiate. Right? Wrap that negative 1 around the sine, drop 1 from the exponent, multiply by the derivative of sine. You could go ahead and put pi over 6 in there. You get the slope a lot quicker. Not only will the calculation be easier, the work to get there is quicker. So you got some problems to practice for tomorrow. Same thing as always, I would never expect you to do every single question. Get a good sampling of them. I'm going to hand back your exams here so you can take a look at them if you want.